So a buffer is a solution that's designed to resist the pH changes when a strong acid or a strong base is added to it. A buffer can only consist of a weak acid and its salt, and that salt's going to be its conjugate base, or a weak base and its salt, and that's going to be the conjugate acid. Right at this moment in time, you need to look at those three solutions and figure out which one of them would make a good buffer and which one would not. Here, let me help you out. Notice over class clowns in Hawaii. Does that describe this acid? Name this acid. Phosphoric acid. Is this weak or strong?
Weak.
Weak. And this is its conjugate? Yes, actually it is. Look at it. Phosphoric acid plus water. It donates that proton. So would this make a good buffer? Indeed it would. Name this acid. This is such a simple concept that y'all just don't like. 6 acids you need to be able to name. 6. Perchloric. Perchloric. Weak or strong?
Very strong.
Very strong. So it is a strong acid. All right. And it's not the fact that this is a strong acid that doesn't make it a good buffer. It's the problem with the conjugate base. A conjugate base of a strong acid is weak. And because it's a weak conjugate base, it doesn't make a very good buffer. So, no. And now we have this. This is a weak base, and it's conjugate acid. Does it make a good buffer?
Yes.
Yeah, it does. It does make a good buffer. All right.
So the buffer is like weak acid and weak base? Or good
Weak,
buffer?
it's a weak acid in its conjugate, a weak base in its conjugate. Let's take my favorite weak acid and its conjugate. My favorite weak acid is acetic acid, and its conjugate would be the acetate ion, generally put into a buffer system as sodium acetate. So you take the weak acid and its conjugate base, and you make a buffer solution. This buffer solution is added to something else to attempt to keep the pH of that something else constant. All right, if you were to look at a particulate diagram of that, the sodium acetate in solution is an ionic compound that totally ionizes, furnishing a acetate ion and the sodium ion. Acetic acid minimally dissociates, so there will be some protons, and there will be a few more acetate ions from the acid. But for the most part, there will just be acetic acid. Everybody good there? And it is these two things that comprise the buffer system, and it is those two things that will take care of a strong acid or a strong base. In my own mind, I have a way of thinking about buffers. I will share it with you. It's worked for me. It's kind of simplistic, but here it goes. I always think of a buffer system as defenders of a fort. They are inside the fort. Okay, construct your own fort. Could be medieval. Mine happens to be made of logs. And they are at the gates of the fort. On the outside of the fort are the invaders. And the invaders are protons and hydroxide ions, the strong acid and the strong base. You got that? My defenders, my buffer system, have specific jobs to do. One, let's say, is an archer, and the other one is okay, now I'm thinking Lord of the Rings, so there were the archers on the wall, and then there were those guys that threw the boiling oil over the side, okay, got it? Specific jobs to do. So part of the buffer system will defend against one invader, and the other part of the buffer system will defend against the other. It is your job to look at a buffer system and figure out which part of the buffer will defend against a strong acid or a strong base. Are you ready to be able to do that? Let's look at the two buffer systems that we have outlined here. Here's our weak acid and its conjugate base. You have to look at this and say which member of this duo will defend against a strong acid. If I add an H+, will it be this that keeps the pH? Will this neutralize the strong acid, or will this take care of the strong acid? The conjugate base will take care of the strong acid. The acid invades, the base takes care of it. Now let's say that we have sodium hydroxide added to this buffer system. Will it be this or this that takes care of the invading hydroxide ion? It'll be the acid. Do you get this correlation? A strong base is added, the acid defends. Are we clear? We got that situation under control. All right, and here is a basic buffer system. We have a weak base and its conjugate acid. If I add a proton, what part of this buffering system will help it? An H3 because it is the base. If I add a hydroxide ion, the acid will defend.
Those dissociate completely? Because doesn't a weak base not dissociate all the way? Or if that's a stupid question?
No, it's not. Off camera, let me tell you what happens when you add strong, okay? Now, let's talk about how a buffer works. I think I just did. Okay. All right. You can read this on your own time. We talked about how it changes depending on what's added. If to my acetic acid buffer system, if I added the base, it would be the acid whose concentration would change because it is defending. If to my acetic acid buffer system I added an acid, it would be the conjugate base whose concentration would change because it's the defender. Got it? All right. Now, as long as the concentration of the buffer is much greater than the concentration of the base, as long as the buffer concentration is much greater than the invader, the buffer is going to work. This puts us to the next page, all the way in the middle. Let's talk about buffering effectiveness. All right, you want a buffer to neutralize the invader. And so in order to do that, you have to talk about a couple things. The first of all is the buffering capacity of the buffer. That means how much added acid or added base that can be added to it before it is overrun. If we're still using our fort analogy, the buffering system inside the gates, the number of molecules of the buffer will be overrun if there's a huge number of invaders, yes? Then the buffering capacity of that buffer has been exceeded. So it can only handle a certain amount of invading hydrogen ions or hydroxide ions. What does that depend on? Well, it has to do with the concentration of the buffer. And the other thing that we're going to talk about as well is the range at which the pH range at which the buffer is effective. Those pH meters that we used yesterday have to be stored in a buffer whose pH is 4. In order to calibrate those pH meters, I had to test it with a buffer whose pH is 7 and one whose pH is 10. Each one of those was made of a different combinations of weak acid and conjugate base designed to give a pH specifically in that range. In order to calculate the range at which a buffer will work, the pH range at which a buffer would work, you take the pKa. What's the pKa? The negative log of the Ka. And you add 1 plus or minus either way, and that's your range for the buffer itself. Acetic acid has a Ka of 1.8 times 10 to the negative 5th. Find the range at which acetic acid and sodium acetate buffer will be effective. Are you done? Stand up when you have a pH range, be careful when you move. Ooh. Thank you. Stand up when you know the range at which an acetic acid buffer will be useful. That's it? Okay, the negative log of 1.8 times 10 to the negative 5th is 4.74. This buffer is useful and has a range plus or minus 4.74. 3.74 to 5.74, right?
Yeah.
Okay. Yeah. So I don't think it is any stretch for you to know that a concentrated buffer can take care of more invaders than a dilute buffer, yes? A buffer will be most effective when the ratio of the acid and the base are about the same. And remember, it's a big change in the ratio of acid to base before the pH changes. Now, this brings us back to the top of this page, where we will all pay homage to Mr. Henderson and Mr. Hasselbeck, because they have derived this equation that is a quick way to calculate the pH of a buffer. So the pH of a buffer is equal to the pKa of the acid part of the buffer plus the log of the concentration of the base divided by the concentration of the acid. Take the molarity of the base divided by the molarity of the acid. Remember we're using log base 10 here, log base 10. So there you go there. Add it to the pKa. pKa is negative log of the Ka. That's the pH of the buffer. Are you clear? Okay. I think you should do exercise 1 and 2. Exercise 1 and 2. For those people who are watching this as they were absent, here are the answers to 1 and the answer to